Okay, so this is the Zoom meeting for Physics 231C. We're ending the first week of October. We've been studying chapters 5 and 6 this week and last week. Last week was the first exam, and after the exam was over, people started working on the two chapters, 5 and 6. That continues this week. So this week is actually 2 weeks. And here's the Zoom meeting. So there's a reading quiz due today. It's actually in two parts. There's quiz 4A and 4B, but they're both due today. Those correspond to chapters 5 and 6. And then on Monday is the long problem assignment for, again, divided into two parts for chapters 5 and 6. By the way, in case you ever miss a Zoom meeting, or if you are watching the recordings, these notes that I'm using are published in the supplemental content. So if there's some equation that I talk about and you wrote it down wrong, or you're not sure what you were supposed to write down, you can always look up the notes in the supplemental content. And always the Zoom meetings are recorded and put on the YouTube channel. Now, last week was the first exam, and I never really showed the results of the exam, so let me show that now. So here is some feedback for exam 1. These two graphs show the distribution of grades. There were 12 points possible, and this shows how many students got some number of points. In other words, how many students got a particular score. So, for example, how many students got 12 out of 12? Well, actually, quite a few. Looks like about 27 students got 12 out of 12, and a lot got 11 out of 12 or 10 out of 12, and then the distribution stretches down into lower grades, lower scores. Now, if you did the correction exam, because that's already finished, anybody who did the correction exam may have gotten an extra point, extra credit points from the correction exam. Here are the scores on the correction exam. Again, there were 12 points possible. It was the same 12 problems. And the majority, by far the majority of students got 12 out of 12 on the correction exam. So on the timed exam, which had a time limit of 70 minutes, already a lot of people got all 12 problems, but some people got less than 12. On the correction exam, where it was not timed, pretty much everybody got all the questions. Not everybody, but mostly everybody got all of the questions. So the questions were not very hard on this exam. They may be a little harder on the next exams because the material is getting more difficult as we go deeper into physics. I had a Zoom meeting last week on chapter 5. That's really a very important chapter. It's the chapter on energy. And so that had a long problem. That has a long problem assignment due Monday. That's an important chapter. Chapter 6 is a little less important. Why do I say it? Well, we're going to be using the concept of energy throughout the rest of the semester. Chapter 6 is about momentum. We won't be using momentum so much throughout the rest of the semester, a little bit, but energy we'll be using a lot. So chapter 5 is really important. Chapter 6, not so important. Chapter 6 has a particular application, collisions. So when you have objects colliding, the best way to analyze the problem is to use the concepts of momentum. Now, you've probably already read chapter 6. One of the most important equations or ideas in chapter 6, first of all, the definition of momentum. It's something very simple. It's the momentum of an object which is moving is the mass times the velocity. Now, velocity is a vector, mass is a scalar, mass times velocity will be another vector. So momentum is a vector. It has a magnitude and it has a direction. The unit of momentum is, well, the unit of m is kilograms, unit of velocity is meters per second. So the unit of momentum is kilogram meters per second. That doesn't have any special name. Now compare momentum to kinetic energy. Remember, kinetic energy was 1/2 mv squared. So there's that extra factor of 1/2. That's not so important, but it also depends on mass and velocity, actually velocity squared. So that really only depends on the magnitude, not the direction. But it's a different combination of mass and velocity. And of course, kinetic energy is a scalar. So momentum has the vector direction character, but kinetic energy does not have the direction. Now, if an object moves under the influence of a force F, this should really be the net force acting on the object. The change of its momentum is the force times the time during which that change occurred. And this combination is called impulse. So sometimes you'll get a homework problem or an exam problem where you have to use the idea of impulse. You just remember impulse is force times time, kind of unlike work, which is force times distance. This statement is in fact equivalent to Newton's second law. So we could say the change in momentum would be the mass times the change of velocity. Change of velocity is acceleration. Mass times acceleration is time. So, well, actually the change of velocity would be the acceleration times the time. So this equation is just a different way of writing Newton's second law of motion. We've been writing it previously as force is mass times acceleration. Well, you could just as well say force is rate of change of momentum, or you could say the change of momentum over a time interval delta t is the force acting on the object. That really should be the net force times delta t. In fact, this is the way Newton himself wrote the second law of motion. Later on, people started referring to the acceleration. The reason momentum is important is because it's a conserved quantity. If you have two objects interacting with each other by equal and opposite forces, then the combined momentum, the sum of the momenta of the two objects, is zero. No, is constant. And that is in fact equivalent to Newton's third law. This is Newton's second law written in terms of momentum. This is Newton's third law written in terms of momentum. Now, we saw Newton's third law back in chapter 5. for every action, there's an equal but opposite reaction. Well, that means if the change of momentum of one object is delta P1 and the change of momentum of another object is delta P2, the combined change is zero. So delta P1 is the force acting on object 1 exerted by object 2 times the time. And delta P2 is the force acting on object 2 exerted by the first object times the same time, because the forces are acting simultaneously. And Newton's third law, action and reaction, we've written before in terms of forces. F12 is negative F21, because these are equal in magnitude, opposite in direction as vectors. I guess I really ought to put a vector sign over this. Well, I ought to put vector signs everywhere, I guess. Now, if we add the change of momentum of the first object plus the change of momentum of the second object, well, we have F12 plus F21. That's F12 minus F12. That's 0 times delta T, but 0 times delta T is still 0. So the change of the combined momentum is 0. So if one object gains momentum, the other object loses the same amount of momentum. And that's a conservation law. It's sort of like conservation of energy, where energy is conserved if there are conservative forces. In this case, it's a vector conservation law. Now, it's important that you have all the equations. You need to have the equations to do the problems. And so when you read the chapter, you should get the ideas, but also write down the equations in your notebook, because you're going to need to use them. So it's very important to write down, take notes while you're reading the chapter, write down the necessary equations. And here are the notes that I would take while reading the chapter. And you see it's a pretty long list. You know, I would say that for each chapter, you should have about a page of notes that you take while reading the chapter. 1 page front and back, handwritten. So, for example, the first section is called Introduction to Momentum. There's the definition, mass times velocity. There's Newton's second law written in terms of momentum. The net force is the rate of change of momentum. The kinetic energy can be related to momentum. Kinetic energy is P squared over 2m. You know, both P and K are related to V, so you can relate them to each other. So this is the equation that relates kinetic energy and momentum. Then there's this jargon called impulse. Impulse, I think in the book they call it J, is the force times the distance. Sorry, the force times the time. And by this equation, the force times the time is the momentum, or is the change of momentum. So the impulse is the same as the change of momentum, but sometimes it's easier to calculate force times time than it is to calculate change of momentum. Section 2 is about the conservation law for an isolated system. The change of one object is equal but opposite to the change of the other object. That's equivalent to Newton's third law, and that says the total momentum is constant. Section 3 is on collisions and explosions. Collisions and explosions are isolated systems. I mean, in a collision, you have an object, number 1, and it's going to collide with another object, number 2. Let's say number 1 is going in this direction. It's going to bump into number 2. That's a collision. And the important understanding is that the total momentum, the momentum before the collision, the total momentum is constant. So the momentum before the collision is the same as the momentum after the collision. And in some problems, that's all you need to know in order to analyze the collision. There are different kinds of collisions: elastic, inelastic, perfectly inelastic. Here are some important equations that you can use in some of the homework problems, probably on an exam problem. When you have motion in one dimension, one object is moving in one dimension, the other object is at rest, and then there'll be a collision. But it's elastic. Elastic means the kinetic energy before and after the collision is the same. So in all collisions, momentum is conserved. In elastic collisions, kinetic energy is conserved. But there are also inelastic collisions where kinetic energy is not conserved. But for an elastic collision in one dimension, you have this mass m1, you have this mass m2, and you have this initial speed v0, and it's heading for a head-on collision, so it'll all stay in one dimension. What are the speeds after the collision? What's v1 after the collision? What's v2 after the collision? Well, that's given by these equations. It's a little bit hard to calculate the speeds directly from the conservation laws. It's a lot easier to use these formulas, which were obtained from the conservation laws. So these are the kind of equations which you might write down in your notebook, because you're going to need to use them. Section 4, it doesn't have the same name as section 1, so there's something wrong here. I know. Section 4 is collisions and explosions in 2 dimensions. Well, then things become more complicated because you have to take into account the vectors, the directions. But again, you have momentum conservation always in a collision or in an explosion. In elastic collisions, you also have kinetic energy is the same before and after the collision. What's easier is an inelastic collision where the 2 objects actually stick together after the collision, like a collision between 2 sticky, two objects surrounded by Velcro. Well, they'll stick together. Then you don't need then energy is not conserved. Energy is not conserved in an inelastic collision, but momentum is still conserved. So you can use the momentum equation where the initial momentum is the sum of 2 momenta. The final momentum is just one momentum, the momentum of the 2 things stuck together. So make sure you understand these equations. You can look on the summary page, the last page in the chapter, to see what are the equations that the authors thought should be written down. But anyway, I would say as you're reading the chapter, write down equations like this. Now, in the Zoom meeting, we usually go over some of the problems for the next problem assignment. Well, of course, problem assignment 5, chapter 5, which is called 4A, is due Monday, but also 4B is due Monday. So let's go over some problems from problem set 4B from chapter 6. So here's problem number 70 in chapter 6. 2 pendulums hang side by side. One mass, M1, is pulled aside until the string is horizontal up here. Then it's released, it swings down and undergoes a collision with the second bob. So it's swinging down here. And it's going to swing down. They have the same length. So they will undergo a one-dimensional collision. And we'll assume it's elastic. So these bobs are, I don't know, made of steel or something. Then this will be pushed forward. This will bounce backwards because of Newton's third law, or because of the conservation of momentum. So you'll have here an inelastic collision in one dimension, namely the perpendicular dimension, the horizontal dimension, elastic. So you can analyze the collision. Well, but first you have to figure out the velocity of this mass m1. That you can analyze from conservation of energy. As this swings down, energy is conserved. So we use conservation of energy to determine the speed at the bottom. Then we use conservation of momentum when they collide at the bottom. Then this one will swing back up. The other one will swing back in the other direction, back up. For those motions, we'll use conservation of energy. So we sort of have three parts to the problem. We have conservation of energy when this is swinging down. And that says 1/2 m1 v0 squared is m1gl. If it's up at this point, it's at height L, it's at elevation L, so its potential energy is mgl. Well, its kinetic energy at the bottom will be exactly the same by conservation of energy. So that's 1/2 mv0 squared, where v0 is the velocity when they collide. Just before the collision, this has velocity v0. 1/2 mv0 squared is mgl, so v0 is the square root of 2gl. Okay, now they're going to go to the collision. That's part two. m1 v0 is m1 v1 plus m2 v2. Momentum is conserved. 1/2 m1 v0 squared is 1/2 m1 v1 squared plus 1/2 m2 v2 squared. That's elastic. So momentum is conserved, energy is conserved, kinetic energy is conserved. So now you have an algebra problem. You have two equations with two unknowns. So you have to solve for v1 and v2. Now, actually, that's done for you in the book. So here are those equations on page 121, which tells you the final velocities in an perfectly elastic collision in one dimension, a head-on collision. So you don't actually have to solve these equations. You've already got the solution on page 121. So now you've calculated v1 and v2. Now, after the collision, that's part three, m2 starts going up, m1 starts going up, attached to a string. So again, you can use conservation of energy. 1/2 m2 v2 squared is m2gy2, the final height of the second mass. 1/2 m1 v1 squared is m1gy1, the final height of the first mass. So you use part two to calculate v1 and v2. You use part three to calculate y1 and y2. That's the question in the problem. So as the masses swing up, 1/2 m1 v1 squared is m1g y1 max. So you can solve for y1 max. It'll be the square root of 2g. No, it'll be, cancel the m1s. It'll be v1 squared over 2g. It'll be y1. Similarly for y2. Where this is the height, the highest point it reaches, the height where the kinetic energy is zero. All the energy has been converted into potential energy. Here's another problem from the problem set. It's problem 123 in chapter 6. It's about Canada's can do nuclear reactions use heavy water to slow neutrons. In order to get a nuclear reaction to occur, the neutron hits a uranium nucleus, and it has to be moving slow enough that it'll split the uranium nucleus. That releases energy and releases additional neutrons. Those additional neutrons will hit other uranium nuclei, split them, that'll release even more neutrons, so you get a chain reaction. The question is, how do you slow down the neutrons that come out of the nuclear reaction? Because they'll be moving very fast. So you produce fast neutrons, you have to slow them down. They use heavy water to slow them down. So a neutron has a certain mass, 1.67. It collides with a deuterium nucleus in the heavy water, because heavy water is H2O. Just like water, it's H2O. But the hydrogens, some of the hydrogens are not ordinary hydrogen, they're deuterium. They're an isotope of hydrogen with twice the mass of a hydrogen. And so a neutron will hit one of those deuterium nuclei. So the mass there is 2 times 1.67, 3.34. Of course, when they undergo a collision, they slow down. If they undergo many collisions, they'll slow down until they're going slow enough that they can induce another fission and keep the chain reaction going. So the problem is, consider a head-on elastic collision with initial neutron energy V0 and the deuteron at rest. So it's once again those same equations from page 121. So one-dimensional elastic collision. And the masses are known, 1.67 and 3.34. There are powers of 10 to keep track of. Now, the question is, what's the neutron speed after the collision? So here's the, we always draw a picture of a physics problem before we start to work it. Well, here's the picture. Before the collision, we have the neutron with velocity v0 and the deuteron just with velocity 0. After the collision, the neutron will bounce back and the deuteron will move forward. So they'll have different velocities, v1 and v2. You can calculate v1 and v2 using these equations, which come from conservation of momentum and energy. You assume the collision is elastic. So those equations from page 121 will tell you v1 and v2. They come from these conservation laws. Now, in particular, the question is, what's the neutron speed after the collision? Well, it's just v1. It's just this v1. Now, m1 is 1.67, m2 is 3.34, which is 2 times m1. So the numerator here will be 1 minus 2 times m1, will be minus m1. The denominator will be 1 plus 2 times m1. It'll be 3 times m1. So v1 will just be minus 1/3 of v0. So in other words, in this collision, the neutron will lose 2/3 of its velocity. If you want to see where these equations come from, I don't know if they're explained in the book, maybe they are, but it's not too difficult to see that these equations just follow from these conservation laws. We can just check the algebra on that. If I move this to the other side of the equation and divide out m1, then I get v0 minus v1 is m2 over m1 v2. So that's this equation. Now, if I look at this equation and divide out m1 and cancel all the halves, I get v0 squared minus v1 squared is v2 squared. No, m2 divided by m1, because I divided it by m1. So V0 squared minus V1 squared is M2 over M1 V2 squared. Now, if I use this equation for V2, that's V0 minus V1. So V2 squared is V0 minus V1 squared times M1 squared over M2 squared times M2 over M1 gives me M1 over M2 V0 minus V1 squared. Now, if you think back to high school algebra, V0 squared minus V0 minus V1 squared is V0 minus V1 times V0 plus V1. Well, the V0 minus V1 will cancel 1 power of V0 minus V1. So then I'll have the V0 plus V1 factor, M2 over M1, and then the leftover factor of V1 minus V0 minus V1. Now, this is just a simple equation for V1. So you solve that for V1. V1 will be proportional to V0 and this ratio involving the masses. So that tells you V1, that's this equation. And as for V2, you just get V2 from this equation. So that'll give you this equation. All right, so any questions? I don't see any questions on the chat. So let's go on to a third problem. This is the collision between a tennis ball and a basketball. If you hold a basketball and a tennis ball on top of it, and you drop them onto the ground, you drop them simultaneously onto the ground, what you'll find is that the tennis ball will shoot way up in the air. You know, suppose you just drop a basketball from some height down to the ground. Well, it'll come back more or less to the same height. Actually, it'll lose a little bit of energy when it hits the ground, but to a first approximation, it'll come back to about the same height as the height where you dropped it from. Or if you did the same thing with the tennis ball, if you held the tennis ball at a certain height, you dropped it, it'd go down, bounce off the ground, and come back more or less to the same height where you dropped it from. But if you drop them together like this, with the basketball below the tennis ball, when they hit the ground, the tennis ball will go shooting up much higher than the initial height. There's a demonstration of this, which is on YouTube, and it's mentioned in the problem statement. You can watch the demonstration. Well, let's see if we can analyze this. What's going on? Well, it's again a kind of a three-step process like we had in that pendulum problem. The first step is the two balls fall together until the basketball hits the ground. Every object falls in Earth's gravity with acceleration 9.81 meters per second squared. So as they fall down to the ground, they'll both have the same acceleration. They'll both fall together. They'll still be right next to each other when the basketball hits the ground. The tennis ball will never hit the ground. So just before hitting the ground, basketball has a velocity v. Let's say downward is negative, so upward is positive. So the velocity of the basketball will be minus 2g times the distance that it's fallen. How far has it fallen? Well, if I call y0 the height of the center didn't hit the ground. It was just the bottom of the basketball hit the ground. So if I take this distance, the height of the center minus the radius of the basketball, that'll be how far it's fallen when it hits the ground. So the velocity will be minus the square root of 2g y0 minus r. And the tennis ball have exactly the same velocity by Galileo. All objects fall with the same acceleration. Step number 2, the basketball bounces off the ground and hits the tennis ball. That's a collision. So just after hitting the ground, the basketball has hit the ground. It's now moving up. The tennis ball, this is just before the tennis ball has been hit by the basketball, so it's still moving down. So let's call this velocity V0. That's the velocity of the basketball. It's now moving up. It doesn't lose much energy when it hits the ground, so we'll neglect any kind of inelasticity. It'll just have the same speed, only now moving up. Square root of 2g y0 minus r. And this is just before the collision occurs, so the tennis ball is still moving down with the same velocity it had before. This velocity I'll call minus v0. It's downward, so it's what I had before, just exactly what I had before. Negative the square root of 2g y0 minus r. Well, that's just minus v0. So now you have the basketball traveling with a certain speed, undergoing a head-on collision with the tennis ball, which has exactly the same speed, but they're moving in opposite directions. So this is a collision between a heavy object, namely a basketball, and a lightweight object, namely a tennis ball. That's the third part of the problem, after the balls collide. After the balls collide, you'll have the basketball moving up and the tennis ball moving up. The tennis ball has been bounced up by the basketball. Basketball loses a little bit of energy. The tennis ball gains a lot of energy from the collision. What you want to know is, how high does the tennis ball go? Well, if you know its initial velocity, you can figure out how high it goes by conservation of energy. But first we have to figure out what are V1 and V2. Well, again, it's an elastic one-dimensional collision, so the momentum is conserved. M1V1 plus M2V2 is the momentum of this pair. It's the same as the momentum before the collision. So that's minus M1V0 plus M2V0. So this is the momentum, total momentum just after the collision and just before the collision. They're equal. That's the conservation law. And the kinetic energy is equal too. So 1/2 M1V1 squared plus 1/2 M2V2 squared, that's the kinetic energy of the whole system, is the kinetic energy of this system, which will be 1/2 M1V0 squared plus 1/2 M2V0 squared. In other words, 1/2 M1 plus M2V0 squared. So here we have, again, two equations with two unknowns. The two unknowns are V1 and V2. It's not quite the same as the collision we considered before, because in the collision we considered before, one object was at rest before the collision. But here's a case where before the collision, both objects are moving with the same speed, moving towards each other. It's not a head-on collision with an object at rest. It's a head-on collision with an object that's moving towards you. So you have to analyze these conservation laws. It's a problem in algebra. You could solve for V1, you could solve for V2. The question asks, how high will the tennis ball go? So you only really need V1. So you solve for V1 by algebra. And then how high will the tennis ball go? Well, as it's going up, energy is conserved. So its kinetic energy, 1/2 M1V1 squared, plus its potential energy, mgy1. What's y1? Well, y1 is the diameter of the basketball plus the radius of the tennis ball. So y1 is the position of the center of the tennis ball. It'll be one basketball diameter plus one tennis ball radius. That's y1. And now it'll move up like a projectile until its kinetic energy reaches zero. When the kinetic energy is zero, then all the energy is in the form of potential energy. It'll have potential energy, M1GH, where H is how high will the tennis ball go. That's how high the center of the tennis ball is, because kinetic energy at that height is zero. So you solve this equation for V1, then you evaluate this quantity to calculate H. And what you find is H will be very large. And you can watch the YouTube demonstration a guy comes out with a basketball, I guess it's a physics teacher. A physics teacher comes out of the high school with a basketball and a tennis ball, and he drops them like this. And the tennis ball goes shooting way up into the air. All right, so here's another problem about Rutherford scattering. We had a problem on Rutherford scattering on the exam. Not exactly the same as this problem. So Rutherford scattering is a scattering of a helium nucleus with a gold nucleus. So, it's again a problem with conservation laws. This problem was not assigned on the problem set. However, a similar problem was assigned. So you might find it useful to look at this. It's a collision in 2 dimensions because the helium nucleus comes, hits the gold nucleus, and goes off at an angle. And of course, the gold nucleus recoils at an angle. So you see, now I have a 2-dimensional problem. So this is a 2-dimensional collision. And I won't go over this today because this isn't really the problem that was assigned, but there's a similar problem assigned on the actually it's quite similar now that I think about it. So I shouldn't say it's not assigned. Well, it's not exactly, yeah, it is. It's exactly this problem is assigned. I guess it's a problem in chapter 6. I guess it's 6. Well, I don't know what the number is, but that is a problem which is assigned on the assignment. How do you solve this problem? Well, it's always the same. You first draw a picture, then you write down the equations, then you analyze the equations with algebra, then you plug in the numbers. So in this problem, you have to calculate V1 and V2, the speed of the 2 isotopes after the collision. You get that from conservation laws. So here's a conservation law in the x direction of momentum. Here's a conservation law of momentum in the y direction. Here's a conservation of energy because it's an elastic collision. Now, of course, you have 3 equations with 3 unknowns because you have now 2 dimensions. So it's more difficult than the 1-dimensional collision. But anyway, it's still just algebra. So the rest is algebra, but it's not very easy algebra. So, you have these 3 equations. This sort of shows how you can do the algebra. At least one way you can do the algebra. I'm not sure this is the best way. You get a quadratic equation, I guess. Well, there are different ways to solve this, but in the end, it's just algebra. But maybe this is the easiest way to solve it. And that will solve one of the problems on the problem set number 4B. All right, so any questions about momentum or about last week, energy? You can either just type it into the meeting chat or you can unmute your microphone and speak up. Well, okay, then I will stop the recording.